My name is Al Newman from Technical Consultants, Longboat Key, Florida. And you're ready to embark upon the Geometric Tolerancing Applications Program. And before you start this applications program, what I'd like to do is just do a little review, a little fundamental review of the basic geometric tolerancing principles. Things that you're going to need, things that are important to know before you enter the applications program. In this applications program, you're going to have to apply geometric tolerancing to a variety of parts and assemblies. They're going to start off kind of simple, and as they get a little further, they're going to be a little bit more complicated. Now, what's important is that you have these basic fundamentals. So this is more of an advanced course, so in application, so I'm not going to do too much of a review. And all of you should have this geometric tolerancing workbook. This here is the fundamentals workbook by Al Newman, by myself, and this covers the basic fundamentals. And it has chapters, and from time to time through the program, I'm going to point out that you can find some of that information in various pages in this book. Now, there's an accompanying pocket guide that goes along with this. So if you haven't had some fundamentals, you should at least review this book or review some book, you know, that it has the fundamentals, because I won't be reviewing too much fundamentals. I'm expecting you to understand these principles as we go along. So let's get started. Here's a picture of the workbook I just put up on slides so you would have it. There's an accompanying pocket guide that goes along with it that covers some of the basic principles. Those are all available from TCI in Longboat Key, Florida. Now, to start off, these are our geometric characteristic symbols, a little bit of a review. All these symbols you should be familiar with, and these are all of our geometric characteristic symbols. And we're going to use just about all of them here. I guess it's important to recognize here these are our form tolerances, right? These are the ones that have form. There's no datums allowed with these. These are for individual features. So you should have your workbook, your fundamentals workbook open, and on the rear of the fundamentals workbook kind of gives you a guideline, and we'll show you all of these symbols, when you can put modifiers, and what the tolerance zone looks like. This here is so this is for form tolerance, no datums with these. We're going to use flatness quite extensively. We're going to talk about some of the other ones, also circularity, roundness, some of those. And then one of the big ones, the biggest one we're going to do, the big kahuna here, is the profile. We're going to use a lot of profile tolerance. Remember what profile tolerance is. Profile tolerance locates surfaces. You have features that have size, and then you have features that don't have size. And we're going to apply profile to surfaces. It's going to replace plus or minus. Plus or minus tolerancing in this application program is just for the size of something. The size of a hole, the size of a tab, the size of a pin, or maybe the thickness of a plate. As soon as you want to start locating things, you want to locate surfaces, we're going to use profile. So there's going to be extensive use of profile. We're going to use geometric tolerancing and everything. This is a geometrics class, so we're going to use it to its fullest, right? It's a 3D mathematical engineering language. We're going to use profile. So profile is a 3D callout. That's what we're going to use. Not too much on profile of a line. I don't see a lot of use of it. We're going to use a lot of the orientation tolerances. These are our orientation tolerance. Let me circle this one here because I want to make sure you understand that. That's profile. That's our big kahuna there. And then there's orientation tolerances we're going to talk about. In the orientation tolerances, we're going to use perpendicularity. We're going to use parallelism, and I think there's an angularity or two in there. The angularity, all of these tolerances, they're really the same, right? If you really take a look at them, they're all really the same type of tolerance. It's just controlling the orientation of a surface. The angularity is used for something other than 90 and 180. Perpendicularity is 90 degrees. Parallelism and everything that's parallel or 180 degrees. And then there's position. We're going to use a lot of position tolerance, for holes, slots, tabs, pins, things like that. When it's necessary, we're going to use position. Concentricity we will not use. I don't have much of a use for concentricity myself. I have a hard time finding any use for it. Symmetry, not either. There will not be too much in the book. There will be some on runout. We will talk about runout a little bit. And there's a circular runout, and then there's the total runout. Circular runout is a 2D tolerance, and total runout is a 3D. So these are our geometric characteristic symbols. You should be familiar with those. Like I said, this is more of an applications class, and you should be familiar with that already. And fundamentally you should be familiar with all of these symbols. All right, let's go on. I guess geometric tolerancing. Geometric tolerancing is a 3D tolerancing system. We want to think 3D. We want to be able to establish a datum reference frame, and geometric tolerancing requires us to establish a datum reference frame. We're going to put a datum reference frame on a part. And you know, a datum reference frame is just a fundamental principle of our X, Y, Z Cartesian coordinate system that's in our CAD systems, in our manufacturing systems, in our quality systems, coordinate measurement machines, manufacturing. So we want to be able to establish the Cartesian coordinate system, the datum reference frame on the part. Every part has got to have a datum reference frame. We've got to know where it is, no more implied. We want to be able to call it off. This is 3D tolerancing. Geometric tolerancing is 3D. All right, and it's based on the ASME Y14 standard and the ASME Y1451 mathematical definition standard. All right, this here is our datum reference frame, and we're going to establish a datum reference frame on every part that we do, and that's going to be key. That's paramount. One of the first things we're going to do is when we're looking at parts, where is the datum reference frame? So we want to establish that datum reference frame. And a datum reference frame, if you remember, what it's established with 3 mutually perpendicular planes. You know, I have a plane here, I have a plane here, and I have a plane over here. When I have the intersection of 2 planes, you're going to have a line. And where I have the intersection of 2 planes, I have a line, and intersection of 2 planes, I have a line. And where they all intersect, I have a point. So the datum reference frame then consists of points, lines, and planes. And we want to be able to establish this datum reference frame on every part. So when I talk about an axis, you know, there'll be this part of the datum reference frame, the axis, and so on. All right. So points, lines, and planes. We want to remember that. And you know, in the fundamentals workbook, if you're not familiar with datums enough, you want to take a look in the fundamentals workbook. That's chapter 5 talks about datums. Chapter 6 will talk in the fundamentals workbook. It'll talk about modifiers, which you will want to know something about modifiers also. All right, when to use maximum material, least material, regardless of size. In many cases on the drawings, you're going to be required to be able to select the datums, and after you select the datums, you're going to have to apply modifiers. And so what this is we're going to talk a little bit about, when should you use MMC, LMC, or RFS. And this example here is in the fundamentals workbook, and we'll give you some guidelines when you should apply the, you know, when you're using a position tolerance up here, when should you apply the modifiers. And remember the different modifiers that you could have. You could have inside there when you're using position, you could have an M, you could have an L, or you could have an implied regardless of size. Remember our rules say that if nothing is stated inside the feature control frame, it's going to be implied regardless of size. You should be familiar with all of those rules also. That would go for all of the orientation form tolerances also. So when would you apply? What symbol would you apply? So here happens to be a real simple part there up on top. You see on the right hand face it's datum A, on the bottom it's datum B, and then on the left side it's datum C. And it looks like I have basic dimensions locating that hole. And then the question is well, should you use an M in there, or should you use an L in there, or should you use an S? Well, it depends what the part does. You know, what is it that you're interested in? So which modifier you would use. And so on this particular example, I showed 3 different particular applications of when I would use which symbol. So what I'd like to do is go through each one of those a little bit with you, kind of briefly, to familiarize you with it, just a review for you. So let's take a look at the first one. And so there's 3 different applications. That part could fit 3 different ways, depending on how it goes, is what modifier you use. So let's take a look at this first one. This one here is maximum material condition. And if I had a maximum material condition modifier, you notice in here, this is my datum, this here is datum A, right? This face here is we'll call off as datum B, and this one here is datum C. I want to set up that datum reference frame. Why we selected those datums, this is the origin of the coordinate system. Why we selected them is, see, because that's the way the part fits inside of the assembly. This is the green assembly that it fits in. And this hole, what is the purpose of that hole? Remember back in plus or minus days, you would just point to a hole, and there's a hole, and It's a hole. It had plus or minus. Didn't matter what the hole was for. It just had a plus or minus. Now with geometric tolerancing, we have to think about it a little bit more. What are you using that hole for? Well, in this case here, let's say this here is our orange part. It fits into this assembly, and we would like to clear this purple pin. You see that purple pin? We have to clear it. And that purple pin is pressed into the base, into this green base. And this part here, our orange part, just fits into that. You know, it rests on that face, down in this corner, fits in there like a little shoe down in that corner. And when it fits in, what we'd like to do with that hole, the purpose of that hole, is to clear that purple pin. That's all you want to do, is clear the purple pin. If that's what you're interested in doing, you know, that would be like a nut or a bolt, you know, that you're trying to clear the purple pin. This would be, to me, appropriate to use maximum material condition. And why you would use maximum material condition is you know how that works. It says when the hole is at maximum material would be the smallest size, 500, it can move around 10. As the hole goes to 502, now the hole, since it got larger in size, it can move around more. It can now move around 12. And to me, that's appropriate for this pin. You see, you're just trying to clear that pin. So basically what it's saying, if you have a small hole, the hole has to be on center. If the hole gets a little bit larger, you see how much it could be off the center? See where the center of that hole is? Center is over there. If the hole gets larger, you see, then it can be over here. So if you're just using a hole for clearance, this here is a good one for maximum material condition. So I would use maximum material condition on something like that. All right, now let's take a look at another example. Now this here is another part, and let's see, where are datums here? Datums is the bottom, back face is A, this one here is B, this one here is C, just like we had before. And the reason is it fits into an assembly. Fits into this assembly just like before. But this time, do you notice, we're not clearing the pin. You see that purple pin? The purple pin is pressed into the hole, into this part. Wherever that hole is, that's where the pin would be. So in this case here, we're not clearing. Remember the last time what the purple pin was pressed into the base, and this hole was clearance. This time, this pin is pressed into that hole. And now you'd like to know where the pin will be. Well, where will the pin be? The pin will be wherever the hole is. You know what happens. What happens if the hole gets larger? If the hole happens to get larger in size, right, gets larger in size like this, then what happens? The pin just expands and finds the center of it, right? So wherever the hole is, that's where the pin is going to be. So to me, whenever you have press fits, you have interference fits, that would be a regardless of feature size, or where location is important. And remember, the way you would specify it, if you put no modifier in here, then you're implying that you want regardless of size, right? It's one of those modifiers would be in there. If nothing is stated, then it's implied regardless of size. So if I had this type of application where press, interference fits, or where location was very important, I would use regardless of size. So this would be a regardless of size application. All right, let's take a look at our next slide. And next slide here would be this one. Now this one here is a little different. This one here is least material. Now let's take a look at the application. Well, where's our datums again? A, it looks like it's this side. This one here is B, and this side here is datum C. And the reason is the datums were selected the same because it fits inside this little corner again, like a little shoe. Now it fits in. Now this time, what are we using that hole for? Well, let's take a look at the application. You see I have a, well, let's say like a little pilot pin. And this pilot pin fits inside of that hole. Now over here, you see what I did is it's a cross section, a section I cut over here, so you don't see the head. If you didn't see the head, you wouldn't see the hole. So this is a cross section. Now this pin fits inside of this hole. And when it fits inside of that hole, this hole locates the pin. We are interested in where this pin is going to be. It's not a clearance. It's not a press fit. Wherever that hole is, that's where the pin is. The reason we put that hole in, the reason the engineer called off this hole, right? The reason that hole is in that plate is its purpose is to locate this purple pin. Now, this would be an application possibly here for least material. Now, least material, what does least material say? Least material would say when the hole is at its least material. And what is its least material? Least material is 502. When the hole comes in at 502, this hole can move around 10 thousandths. But what it says is when the hole comes in at 500, it's a smaller hole, it departed from least material, now the hole can move around 12 thousandths. Now, how does least material work? Well, you see, if the engineer is putting this purple pin inside of the hole, this is what he's saying. He says when you take that pin and you put it inside the hole, when the hole is at its largest size, 502, that's when you're going to take that purple pin, you put it in, it rattles around inside of the hole, right? because it's a larger hole. What he's saying is that at the larger size, that hole can move 10, right? Because I have to worry about the rattle of the pin inside of the hole. But when the hole comes in a little bit smaller, you see, rather than a 502 hole, the hole comes in at 500. When you put the purple pin inside of the hole, well, the size is smaller, so it doesn't rattle around as much. Well, then you can be off by the amount that the hole got smaller by. So basically what you're telling manufacturing is, look, you're putting a hole in here for me. I got this purple pin that fits in a hole. If you make a big hole, then when I put my pin in, it rattles around, right? And I'm trying to keep it on center as much as possible. So I'll tell you what, if you make a smaller hole, you make the hole smaller, you can be off more than when you make a big hole, right? Because remember, when the engineer is trying to figure out how much that hole can be off location, or that pin can be off location, there's two things that affect the location. Not just the location tolerance you put here, but it's the size tolerance also. What imagine is that if they took a hole and put it right on center, perfect, it was zero position, but you put a great big hole in there, can you imagine you put your pin in, it's going to rattle around. So what the engineer is saying here again is, look, when you have a large hole, I want you on the center within 10. But if you make the hole smaller, well, then what it does is the pin, when I put it in, doesn't rattle as much. I'll allow you to be off location more. So least material is some places used when we're going to locate things, right? So that's where I would use least material. Now, I use a limited amount of least material applications in the program. I tell you where you can use it. I'm worried about sometimes people applying least material all over because it certainly wouldn't work if this was a clearance hole, would it? I mean, that would not work at all. If you ever had clearance holes, you would never use it. And sometimes people get confused. They put LMC on the pin and then they put MMC on the hole, and you would never do that either. They would never have where one was L and one was an M. You know, if you were designing two parts to go together, they're going to both be probably, most of the cases, both maximum material or least material. So least material would not be good for locating, for clearance holes. All right, that gives you a little bit of review on that. And remember, there's more in the Geometric Tolerancing Fundamentals workbook that you'll find in Chapter 2, where I talk about it. And there's, I don't know, about 10 pages where it talks, and it even shows a little calculation, you know, a little stack on, you know, the difference between maximum material, least material, and regardless of size. So if you're not familiar with that, you might want to review that a little bit. All right, let's go on. Continuing here with our review. Now here's another case that these are little things that I see people sometimes having a little trouble with. That's why I thought I'd do this little bit of a review. You're going to have some examples in the workbook where you're going to have a shaft. There's going to be a few of them where you're going to get the shaft. And this here is a part, this yellow one. You see I have one diameter on this side, and then I have a diameter on the other side. This one has size, and this one has size, of course. So this one here is called off as a datum. The small one is a datum. That's going to be. Now, if I want to keep this one on the center, what symbol should I use? Right? There's a number of symbols you could use. One is you could use the position symbol. Right? That's possible. Another one you could use would be runout. Now, there's two kinds of runout. There's what we call total runout, and there's what we call circular runout. And you notice I put next to it just a little memory jogger. That's a surface to an axis. Position is an axis to an axis control. And I guess another symbol you could use would be concentricity. That would be another symbol. And then another one you could use would be profile. So these are different ways that you could keep this thing on the center. Now, all of this diameter you want on the center. Now, you notice I put this little memory jogger here that position is an axis to an axis control. Runout, what that is surface to an axis. And then concentricity, that's median points to an axis. And concentricity, let me tell you here that I'm not a big fan of concentricity. I don't like it. I don't use it. You won't see it in my program. And I'll show you what it is, and I'll let you be the judge. You use it. It's up to you where you want to use it. Okay, and then there is profile control. And profile, we have a profile of a surface, which is 3D, and profile of a line, which is 2D. And, you know, profile of a line is usually used for 2D parts like extrusions, things like that. So it's not a very common one. So profile of a surface is the one that we'd be using. So what I'd like to do is to compare these. Now, profile of a surface, that's the same thing, surface to an axis. You say that's the same thing here as runout, but what the difference is, profile includes the size. So let me talk about these here a little bit, so compare them so you can clearly understand the difference between them. All right, now let's compare those. Now when you're comparing them, you look at them, you say, look, I want one diameter on the center of the other, and if I want one diameter on the center of the other, well, what's the difference? It just one's on the center, the other one's on the center. Well, sometimes to understand that a little bit, I'm going to show you what the manufactured part actually looks like. And the manufactured part really looks like this. When you see it has, this here is in all of its ugliness, and you know, that you show it up on the top drawing, and it, you know, it tells you a size, and but it doesn't really look like that, right? It could be a little bit oval, it could be out of round, it could have lumps and bumps on it, it could be bent. This is what the part looks like. So this is the way you want to think. You don't want to think like that. You want to think like this, because this is your actual manufactured part. Okay, now first of all, let's take a look at our datum, the datum axis. And how is the datum axis established? Now the datum axis up here, this is datum A, and that's going to be the datum for all of them, for all of these different characteristics. Now remember, you would never have all of these on at the same time. I'm comparing one to the other. So datum A, when I call off datum A, what does that mean? Well, datum A says that I have to come in and I have to find the axis of that feature. Remember how I do that. That's in Unit 5, a little review here. What it is, the smallest circumscribed cylinder. Collapse the smallest cylinder you can around it till it just contacts the high points. And when it contacts the high points, you take the axis of that cylinder, right? So you see over here, the smallest cylinder around it. If that thing is oval, that's the best you can do, is grab it, and then we take the axis of that, and that's our datum. So there's our datum axis. And that'll be the way we describe the datum axis for every one of these up here, so I won't keep saying that over and over again. All right, now let's take a look at position. Position, what is position? Position is an axis to an axis control. If it's an axis to an axis control, then what I have to do is I have to find the axis of the feature. And what I'll do is I'll take the smallest cylinder I can collapse around it, and you see that's what I did. I took the smallest cylinder, collapsed it around till I just contact the high points. And when I contact the high points, now I found the axis of that cylinder. That's what position is, axis to an axis. Now once I found the axis, then I have a tolerance zone. And the tolerance zone is 5 thousandths. It's a diameter of 5. So there's a little tube of tolerance, right? And the tube of tolerance looks like this and extends over the length of the feature, and the axis of the feature has to fall within. So you see what happens. See how it can tilt? See that little axis in there? It can tilt up, it can tilt down, it can tilt up and down. Any place it falls inside of that tolerance zone. So that's what position is. What I'm going to do is contact on the high points and see what it is. Now, how would you check something like that? Well, I guess some way to be able to check something like that, you know, what I could do is take this diameter. I'm locating on this diameter, and one way I could do it is just take an indicator and put an indicator on that surface. And if I put an indicator on it, you know, and watch how much the indicator moves. That might be a way to do position. Or there is, you know, I could do it by X and Y. Get on the datum and measure in X and measure in Y. Now, really think about it now. Remember, when you're doing this could be position. You see, if I have a diameter that looks like this and I have a diameter that looks like this, see, they're both oval, but they could have perfect position, right? So you could have two ovals that you know, went oval within the size tolerance. Because what I'm going to do is I'm going to take the smallest cylinder around one, the smallest cylinder around, and you say axis to axis, they're perfect. So if they was to check something like this, they might do it something like this, let's say with an indicator. See, let's say there's your datum axis, and they might hold it in a collar or chuck, and let's say this is our diameter, and the diameter is off center like this. You see how much the diameter is off center, and let's say the center is off by 0.0025. See, it was allowed 5, it comes off within 2.5. If I put an indicator on that surface and I rotate it around and I'm watching this little needle, if the needle never read any more than 5, it's good. Because what would happen, you see, if that thing moved down 2.5, and then back up 2.5. So if it read any more than 5, it's good, right? Now, what would happen if the needle read 6? Well, if the needle read 6, it still could be good. And the reason is that, remember, position does not take care of ovality. So any ovality that you would have on this, you see I have a size tolerance up here that says, the size tolerance that I have here, it says that the tolerance is 202 to 2 inches. If it had any ovality in it, ovality is not part of the equation. So you could actually check it with an indicator, but if you did, if it read 5 or less, it's good. I know it's good. If it's over that, then what you could do is you could evaluate it and maybe map the surface like this, and you would say, all right, here's 0, here's 90, here's 180, and this is 270, and then rotate it around and be able to map it and see what the thing looks like. So the thing is that people think as soon as you use an indicator, that's runout. That has nothing to do with runout, using an indicator to check something. All you're using is using the indicator to collect data, and then after you collect the data, you analyze the data, and then you use it. So that's just to make sure that people think. It says, oh, you're using an indicator, that's runout. That has nothing to do with runout, right? So we could check that with a coordinate measuring machine. You could use an indicator. You're just collecting data, and then you're analyzing the data. So that's position. That's our position call-up. So position is an axis to an axis control. All right, let's take a look at the next one. Next one here is runout. Now, when we have runout, there's two kinds of runout. You see the two kinds of runout? What we have is we have total runout, and then we have circular runout, just basically 2D and 3D. The total runout would control taper. Circular runout doesn't control taper. And what runout is, it's a surface to an axis. You know, it's different than position, which was an axis to an axis. Now, when I say surface to an axis, what does that mean? Well, let's take a look at that. Down here, what you have is a tolerance zone, and a tolerance zone is 5 thousandths. And if you have this tolerance zone of 5 thousandths, the surface has to fall someplace inside of that zone, right? So there's your datum axis, right, established right here on this right down here. There's your datum axis, and then you have a tolerance zone that's 5. So what that would require then is an indicator. I take the indicator and I rotate it on that surface and watch it. Now, do you notice that if this surface was oval, you see what it would do to the indicator? It would make the indicator go crazy, right? Because ovality would also be included in that. Remember a little while ago when we had position, you had one diameter that looked like this, one diameter that looked like this. Those could be perfect position, but runout wouldn't make it runout. So how would you check runout? Well, I'd probably do it the same way. I'd just grab a hold of that diameter, the datum, and then I'd put my indicator on, rotate it, and watch how much the needle moves. If it reads, let's see, our tolerance here is 5. If it reads 5 or less, it's good. If it reads 6, it's out, right? Or remember with position, you would be allowed to be able to further evaluate it, and if ovality was in there, you could take it out, but with runout, it's out, that's it. So which one is tighter, runout or position? Of the two, I would say of the two, it would be runout. Runout would be the tightest, because runout, what it does is it also picks up ovality, where position doesn't take care of ovality. So you don't remember what position is. You take the cylinder, you wrap it around, and you find the axis of the two cylinders. Runout, what you're going to do is you're going to take the datum axis, and then you're going to put an indicator, and you're going to read the surface, just what it says. It says it's a surface to an axis. All right, let's take a look here now. Let's move along. So let me just say that same thing again. I'm going to say the same thing again so you understand it. Sometimes I have to repeat things here. This is like Groundhog Day. And this here is more of a graphic to show you what it looks like. This here is your drawing. You see datum A, this one here I call the big one datum A. And over here I put a position on. I said position within a diametral zone of 4 in relationship to A. But what does that look like? Now this is an excerpt from the workbook, the fundamentals workbook. I kind of blew it up here so you could see it a little bit better. The datum, remember the datum? What we have to do is wrap the smallest cylinder around it. And once we take the smallest cylinder, that's the axis of the true geometric counterpart, theoretical axis. And then position says that you have a diameter tolerance zone of 4. So it's a little tube of tolerance that goes about the axis. And then what you do is you take the datum feature, or I'm sorry, the feature, take the smallest cylinder you can around it, and the axis of that has to fall inside of the zone. So you notice it's an axis to an axis. It has to fall inside of the tolerance zone. So you notice ovality doesn't even come into play when you're looking with position. Okay? All right, let's take a look at runout now. Now remember, there were two kinds of runout. There was what we called circular runout, and there was total. Let's do circular runout first. Datum A. Datum A is the outside diameter, the large diameter. That's our datum, just like before. The smallest cylinder you can wrap around it, we take the datum axis. That's how we create our axis. And remember what runout is, circular runout? I take the indicator, put it at one spot, and I rotate it and watch how much the needle moves. See where it is? There's our tolerance zone. It has to fall inside of that tolerance zone. Circular runout, what we require is move it to a new spot, re-zero the indicator, check it again, make sure it falls within. Take it to another spot, check it again. How many places you check it? You check it for the rest of your life. Well, we have somebody in quality, and he said, well, what do you mean check it the rest of my life? I can't check it the rest of my life. I said, okay, then what's your plan? You would put that information into your quality plan, right? Geometric tolerancing doesn't tell you how to check the part. It just defines what the part has to look like. How you're going to check it, put it down in your plan so we can see it. then we can evaluate how much you want to spend, how much time you want to spend on it. Depends what the tolerance is, the first part, 10th part, whatever. That information is covered there in the fundamentals too. So here is, take a look back at our slide here. That's a runout. You notice it's a circular check. What I'm doing is it's like a 2D check. I'm making a series of circular checks. All right, let's go to the next one here. Next one here is total runout. Now you'll take a look at total runout. See, that's the two arrows. Do you see the tolerance zone here? See the tolerance zone? The tolerance zone is more like a cylindrical zone. First of all, where's our datum? The datum is the large diameter. See, that's our axis. I come along, grab a hold of that axis. And in this surface, I would take the indicator, put it at one spot, and then as it's rotating, I'm sweeping it back and forth, seeing if it falls within the zone. So you see the difference between circular runout and total runout. Total runout would control the taper. Circular runout does not control the taper. You notice it's an axis to a surface, just like we've been saying. There's your datum axis, and then we see if that surface falls inside of the tolerance zone. All right. Now, what I'd like to do is just some practical applications. Sometimes I show it to people, and they say, well, I still don't understand. So let's just try it out here in an example. Here's a practical example now. And these are problems that you might see that you're going to have to apply the tolerancing as you see fit, and then I'm going to show you the solution later on. So here's an example. Here's a housing that I have. I have a bearing, and inside that I have a shaft. This little orange-colored shaft. It goes in, and what it does is it presses on the bearing over here, and then I have a gear, and then I take this gear and I press the gear on the shaft. And you see this? This gear has to match up with another gear. And so what we would like to do is this tolerance, this little orange part right here. So that part is important, because if the gears don't mesh, you know what will happen here. So we're interested in where this diameter is relative to that one. Well, first of all, if you were looking at these two, if that was your part to tolerance, that one, what would you pick as the datum? Right? Would you pick the small one as the datum or the large one as the datum? Which one would you pick? Well, remember, we're going to talk about this when we get into the class a little bit later, but what I would think is that I would pick the small diameter. And the reason I would pick the small diameter is that's the leader, right? When it goes in, it comes in and it locates on the small one, and then the big one is the one that's going to be off, right? That's the way it works. And because if you picked the large one, you said the large one is my datum, and then you're going to tell how much that can be off. When I get the information, how can that one ever be off? That's not the one that's off. Really, the amount of tolerance you put on that side is the one how much this one can be off. So what I do is I always select the datum the way that it mounts, right? And it mounts on this one. This is the leader, right? This is the follower. This is the one that's going to be flopping around. This is the one where it locates. And that's the way we're going to do our applications when we get into our book too, because later on when you're going to do stacks, we're also going to do some stacks. It's going to be very important you do that. All right, so on this drawing then, you see what I did is I called the small one the datum. All right, now on this diameter, knowing our function the way we're looking for this gear, what would you put here? Would that be a position call out, or would that be a run out for what you know? Now I hear a lot of people, they got this little saying, when in doubt use run out, but I wouldn't use that term at all. If I was looking at this and looking at this application, what I would use on this one here would be a position call out. And why I would use position? Because you notice this is the way this part works. First of all, when I take this little idler shaft and I plug it into the hole on the bearing, you see what it does on the datum? It contacts on the high points. Contacts on that. So ovality, this little bearing here doesn't know anything about the ovality. Over here, the same thing. If I took that gear and I pressed the gear on, you see what it does is it contacts on the high points. Ovality is not part of my problem here. What I'm looking for is axis to an axis. And if I'm looking for axis to axis, position call out would be more appropriate. So I would use a position call out on this because I'm contacting on the high points. If I did do a runout would work. I mean, it would work. The only thing is if there was any ovality on the shaft, you notice what it would do is make the needle move up and down, and if the needle moved up and down, well, then you couldn't be off center as much. So to me, this would be appropriate for a position call-out. I would use position on something like this. And you can look at it. When you look at it, it's just like we said. It's an axis to an axis. You see, you're contacting on the axis here and the axis here. So that would be a position. All right, let's take another application. Now I have a pulley here, and then I have another pulley over here, and I have a belt between them. And what I'm looking for is there's no adjustment between these two pulleys. And so I have a little idler wheel, and this idler wheel comes in and puts tension on the belt. And what am I interested in? I'm interested in here is I don't want this belt to flutter up and down. I don't want it to flutter up and down. Don't let it do that. So I'm going to take this idler wheel, I come in. Now this idler wheel has adjustment. It can adjust up and down, and so, you know, as the size changes, I bring it down tighter or looser, I can adjust it up and down. Similar to, you know, an alternator in your car or something like that where you're tightening up the belt. Well, if this is your part, this little blue one, and this is how it works, it mounts on a bearing over here. This is where it mounts. Then what would be the datum? The little diameter or the big one? Well, what I would think, it's the little one, right? You see, that's the leader. See how it mounts? It mounts on here. It mounts on that leader. So that's what I would say is I would say that was the leader. And if I show it over here, that's exactly what I did is I picked the small diameter as the datum. And that's the datum. Because the size here, the ovality here, on this here, it contacts on the high points. Now remember, if I was ever worried about the ovality, as this one or in the bearing that I had before, the idler shaft, you know, you could always put a roundness or you could put a cylindricity on it to control it. But because ovality, just by putting a position on it, wouldn't control it, right? Or you would have to have some kind of tolerance on that. All right, now what do we put on this diameter? What would you put on here? Would you put position or would you put runout on this one? Well, what I would think I would do is I would use runout. And I would use runout, and why I would use runout is because, you see, ovality is going to affect me. If this thing is oval, you see down here, if that diameter is oval, or if it's off the center, any one of those things causes this belt to flutter, and I don't want this belt to flutter up and down. So in this case here, runout would be more appropriate, right? Position wouldn't take care of ovality, so what I would do is I would use a runout on this one. And what would you use on this? Would you use a total runout? Would you use total runout on this, or would you use a circular runout? What I would use here is I would use a total runout. And why I would use a total runout? Because circular runout would allow taper, and if I had just circular run on here, you see how it could run the thing right off the belt. So that would be a total runout on here. All right? All right, let's take another example. We haven't done anything on concentricity yet, and I would like to explain concentricity here. Concentricity, what's the definition of that? That's concentricity is median points to an axis. And when you say median points to an axis, what does that mean? Now, concentricity, let me just say that, well, let me show you what concentricity is. Concentricity looks something like this. Well, first of all, you'd have your datum axis. That's set up the same way, right? The datum is done the same way, you get a datum axis. And you have a diameter tolerance zone of 5,000. There's your tolerance zone of 5,000, right? And it's a cylindrical zone. It extends the full length of the feature. And it says median points to an axis. So if it's median points to an axis, now what I have here is I have cross-sectional median points. And I have to take these cross-sectional median points. You see, as I cut a section here, the halfway point. For example, here, what I'll do is remember what we did with position. It had the smallest cylinder with position. It was the smallest cylinder that I collapsed around the thing, and then I found the center of it. With concentricity, what you would have is two indicators. I would have an indicator on this side and maybe have an indicator on this side. And what I would do is I watched. If both indicators moved out the same amount, then it's on the center. It's concentric. If both indicators moved in the same amount, it's concentric. If one stayed stationary and one moved out, then it's out of concentric at that one spot. For example, let me just cut a section through here. For example, you see, if I went right down from the top here and I went down like this, you see right at this point, halfway point, it looks like the center is really over here. Let's do another one. If I went right across here like this, right to the center, you see how there's a little bit of a gap over here? There's a little bit of gap. Really, the center is over here a little bit. And you're going to get a cloud of median points here. And that cloud of median points has to fall inside of the tolerance zone. Now, personally, functionally, I don't know why I want to know where the cloud of median points is. Concentricity is a very difficult call out to inspect. It's not something that I believe is functional. You know, when parts go in, they contact on the high points. Concentricity is a term that or a symbol that we have in a system that it's not concentricity. In other words, I guess what I'm saying is concentricity is not what you think it is. Sometimes people think, engineers, they say, well, look, I have one diameter, I want it concentric, I want them concentric, I want them on center. But concentricity, if you use it generically, you know, you'd say, well, it's on the center. But when you look at it, this here is a very mathematical standard. And when you look at it, describing it very mathematically, and describes median points. And some time ago our standard says that it's for high-speed rotating parts, but that used to be in an earlier standard and it's not in there anymore. It's just a symbol that I would use position, or I would use runout. I wouldn't use concentricity. The problem is that concentricity is such a generic term, and it's just, you think of it concentric. And so a lot of times new engineers, they say, well, okay, I have two diameters. They look in the standard and they say, oh, concentric. Yeah, I want them concentric, not realizing that, you know, it's a very exotic control, and whether you need that. In our class here, I don't have any problems, and even in our fundamentals workbook, I always try to show an application with it. I really can't figure out when I would use something like that, so I would recommend just not using concentricity. And the same thing with symmetry. When you get to there, we wouldn't use symmetry either. You know, I would use position. If I had a slot, a tab, or something I wanted, you know, on the center, I would use a position call-up. So that's what we're going to use. I won't be using any concentricity at all. All right, so let's go on here. Concentricity is very complex. I recommend using other callouts. And here's, you know, a description of concentricity. Or this is your datum, right? And I say this is concentric. See, the datum would be set up the same way. That's not a problem. It's concentricity. And here's your tube of tolerance, and you have a cloud of median points inside the zone. If you think you have a use for it, you can go ahead and use it, but I don't recommend doing that. All right, let's go on. The last one that we have here is profile tolerance. And profile tolerance, it includes, it's a surface to an axis, it includes the size. So let me show you that here. You notice when profile is used, the dimension becomes basic. You would make that a basic dimension, and there's not any size tolerance on there. And then the surface has to fall inside of a tolerance zone. And this here is your profile zone. So in this case here, this would be a basic dimension. If you have a basic dimension, you have a tolerance zone, right? You have an inner boundary and you have an outer boundary, and the surface has to fall someplace in the zone. Now, if you had something like that, how would you check that? No, heck, I would do that the same way. I'd just take an indicator, right, mount it on the axis, and put an indicator on here. And the difference is I would master the indicator, and I would master the indicator at the basic dimension of 2.001, right? And then I just watch the indicator, and it can move out or it can move in someplace within that zone. Right away, again, people think that, you know, as soon as you use an indicator, what you're doing is you're checking runout. But I could check position, or I could check profile with that too, right? I just master it at that basic dimension, and then as it rotates, I'm watching how much the needle move. You're using the indicator to collect data, so it doesn't have anything to do with runout. And you notice what runout would do is it includes the size. So that means that the largest this thing could ever get then, if it's the basic size here is 2.001, that's the basic size, and I put a profile, and I say a profile within 5, what it does is it allows this thing to have a tolerance on it of plus or minus 5. Now why it's a plus or minus 5 is because, see, if this is your basic dimension, and you have a tolerance zone, this is your tolerance zone of 5, and then you have 5 on the other side, right? So the basic, it can be plus 2.5 on this side, and it can be plus 2.5 on this side. So the largest you could get across here would be plus 5, or it could be minus 5, right? And your tolerance zones here, your tolerance zone is perfectly centered. It's two concentric cylinders, and your tolerance zone is centered about the basic diameter, about the basic center of your datum. All right, here's a bigger rendition of what that looks like. See, there's the datum, the large one. I have a basic, in this case I made it a basic diameter of 1.002. See, and I put a profile on it. I set a profile within 6. So if you have a profile within 6, this is what it looks like in 3D. There's your datum, contacts on the high points. Here's your basic dimension, and your tolerance zone is 6. If that's your tolerance zone across here is 6,000. So what that would be on a diameter, since it's 6 on this side and 6 on this side, on a diameter, that's a total of plus or minus 6, all right, on a diameter. That's your profile. All right, here's another example that I'd like you to look at. In this one here, it looks like some kind of a counter or something. It looks like I have a housing, I have a bearing. I take this little green part, I put it inside the housing. It's located on the bearing. And this here is some type of a wheel. It reminds me of kind of like the anti-lock brakes. You know how I have the anti-lock brakes? I have a sensor up here, and I'm looking how close that sensor gets to the, or how close that wheel gets to the sensor. And you know how that's supposed to work is that if one of the wheels lock up and stops turning, the sensor senses that and then relaxes the pressure on that brake. Well, over here, what we're interested in is that sensor. This is a fixed stop. There's no adjustment on this sensor at all. And what we're looking for is that air gap in here. Now, obviously, if this thing gets too close, it's going to rub. It gets too far away, it's not going to sense. So what we're looking for is we're looking for that air gap in here. There's no adjustment on this sensor at all. So what kind of control would we put on something like this? Well, first of all, where's our datum? Would it be the little one or the big one? Well, I hope you all said the little one, right? Because that's our datum. See how you can tell that's the leader, and this is the one that's going to be off to that. So I would say it's the small one is the leader. And that's what they did. See that small diameter called off as datum A. If that's called off as datum A, what would you put on this surface here? Well, to obtain our requirement, our functional requirement. What I saw that is being a profile tolerance. And I put a profile on it. I'd have a basic dimension, and then I say it's profile. Now, why I put a profile on it, you see, because I'm just looking for the air gap. All I'm interested is don't let this get too small and don't let it get too big, right? That's a profile tolerance, right? There's your datum axis. We're on the datum axis here, and I'm interested in this surface falling inside of a tolerance zone. Now, could you use position on this? Well, I suppose you could use position. The problem is that if you put position on here, you wouldn't be able to have a basic dimension. You'd have to have 2 inches. You'd have to say 2 inches in here, and then you're going to have to put some tolerance on. You're going to have to say plus or minus something. Well, plus or minus what? I don't. But you'd have to. Well, if you wanted no more of a gap than 3, then you'd have to take. Well, I don't know, maybe plus or minus 1, and then you'd have to put. Well, when I want to do that, all I want, look, is I don't want this to get too big, and I don't want to get too small. That's all. That's all I'm interested in. To me, that's a profile. Would runout work? Yeah, I suppose you could put a runout on there, but you got the same problem with runout. Remember, you're going to have to put some size on here. And you're going to have to say that's 2 inches plus or minus what? And I don't know, plus or minus what? You know, how big this thing has to be and how much you can be off the center. Look, just don't let it get too close. Don't let it get too far. So again, is if I make you put runout on here, I'm going to try and make you do an unnatural act. I don't know what to put on here as far as size. There's not a size. It's just when you come from the center, that surface location-wise can't be further or closer than that. That's your zone. Stay in that zone. So to me, that's appropriate for a profile tolerance. All right, let's take a look at the next one here. Now, remember here we were a little while ago, we were looking at this one. This was our gear again. This here is my datum. Remember here a little while ago when we had a position. Well, in position, could we have put a profile on here instead? Right? Could we use profile over here? And we just say profile within 1. Well, no, I don't think you could. And the reason I don't think you could in relationship to A, the reason I don't think you could is you see this size over here? This size, make that a little bit bigger. The size is 0.7505 to 7500. And the reason that's tolerance is so tight because I need that tight to be able to fit inside of the gear. That was a press fit on the gear, so I need this size, right? It's a size that I need to give it a press fit tight. And then the location is another problem. You see what profile would do? Profile, what it would do is it just gives you a boundary, you know, an inner boundary and an outer boundary, and the surface has to fall inside of it. So it includes the size, it includes the location, everything in this one lump sum. So to me, this would not be appropriate for profile. And this would not be appropriate for runout. And the reason it wouldn't be appropriate here for runout, because if I put the indicator on and this thing was oval, the needle starts moving, and then I couldn't be as much off center. So to me, this here is a position call-out. I would use only position on something like that. Runout would not be appropriate there. Okay, let's take a look at this one. Now this here was our call-out that we had a little while ago that was runout. Now, how about on this one? Could you use profile on this one? Remember how we had the idler here? Well, I would say no, you couldn't use profile on this one either. Profile wouldn't be appropriate. Now, why profile would not be appropriate is because you see this pulley has adjustment, or this idler wheel has adjustment. It can get move up and down. In other words, what we're allowing here, the engineer is saying, look, you could make a large wheel or you could make a small wheel. Wherever it is, you just bring it down and you adjust it. So if that was the case, you see we need the adjustment, right? I can have a large size tolerance. You see on this here, that's a plus or minus 10 thousandths on the size. So I'm going to allow you to be large or small, but wherever you come in, I want to put that indicator and make sure that surface falls within the tolerance zone. So to me, this here is run out. Profile wouldn't be used. And I wouldn't use a position because position, right, if the part happens to be oval, Position wouldn't take care of ovality, and I'm interested ovality and off center. Everything comes into play here. So to me, this here is just a runout. So I hope that gives you a little idea here of when to use those different controls, and you're going to need that. If you need to come back and review that again, you can do that here in this. When you're going to come later on, I think you're going to have the mixer, and you're going to have a few other parts that's going to have some shafts in them, and you're going to have to apply some tolerancing to. All right, here's the fastener formulas. Now, the fastener formulas are going to be important when you're going to apply the geometric tolerancing to all of your parts. And when you do put a position on holes, and you put slots and tabs and things like that, you're going to have to come up and you're going to have to calculate a position. So I don't want you to just come in and put the numbers from the air. I want you to calculate these numbers, where they come from. I want to know where every number comes from on here. So this is going to be some very common formulas that you use in the geometric tolerancing for the fixed and floating fastener formulas. And you'll find that information in the geometric tolerancing workbook. I think that's in chapter 15. And it'll show you, and also talk a little bit about projected tolerance zone in there. So you want to, if you're familiar with that, then you don't need to follow it, but ideally you should have that. All right, here's the floating fastener formula. Here's two parts that I want to go together. I have this purple one and I have a green one. And this here is designer parts, right? These are Gucci. And let's see, the datum's on this part. Let's see, on this face here, that was A, this one is B, this one here is C. And down here, that face is A, this one is B, and that one is C. All right, so these two parts to go together. Well, the basic dimensions should correspond, right, from one part to the other. And over here, what size bolt are you planning on using? I have 4 holes. What I'm going to use is a 250 bolt, and it's a 1/4 So if it's a 1/4 bolt, what's the major diameter on that? The major diameter on a 250 bolt, on a 1/4 bolt, would be 250. If you had an M10, then it would be 10 millimeters. So over here, I'm going to take the fastener maximum material. This is your formula here. Then the maximum material condition of formula, the biggest bolt you could ever have would be 250. Then I take a look at the hole, the smallest the hole could get. And the smallest the hole could get is it's 281 plus 6 minus 2. This is a standard clearance hole. You'd want to use a standard clearance hole for the clearance holes. And so the smallest hole is 279. The difference between the 250 bolt and the 279 hole is 29. If you have 29 thousandths worth of tolerance, then the way it works is you could give this one 29, right? That's how I got to 29 here, and I could give this one 29. So you just split the tolerance. That's your clearance. You can have 29 on each one. And this one here, you could also allow maximum material, right? This is clearance holes. This would be a good one. The larger the hole gets, the more it could be off. The larger it gets, the more it could be off. So maximum material would be allowed here. All right, let's take a look at the next one. Next one here is what we call the fixed fastener formula. The fixed fastener formula would be one that went together like this. This would be one where I had 2 parts going together. This is Versace here, parts. They're purple and blue. And this one here is tapped hole. See, the bottom plate is tapped, and then the top part would have a clearance hole in it. So this we call a fixed fastener. See, because the fastener is fixed in one of the plates, it can't move. This is a fixed fastener arrangement. If you were doing the calculations for this, first of all, what size bolt do you want to use? Well, over here it says that we're going to use a 3/8 bolt. If I'm going to use a 3/8 bolt, the major diameter on that would be 375. If it's 375, then I would take the standard clearance hole for that. In this case here, it was a 406 plus 7 minus 2. So the smallest hole was 404. And the difference between the largest fastener and the smallest hole was 29. It just happened to come up like that again. And if it was 29, the difference is you have to split it between the 2 parts. And split it. Now you can split it any way you want, right? Your brother-in-law is making this part, you can give him 28, the other guy gets 1. I wouldn't do that though. I would split it so they're equal, right? So everybody has a chance to do it, to build the parts. So you can split it in any combination, I guess is the moral of the story here. Now what I did is to make them equal. Do you notice I gave the tapped hole a little bit more? Now why did I give the tapped hole a little bit more? I gave the tapped hole a little bit more, I guess, for a couple of reasons. And a couple of reasons here is that one is a tapped hole is a 2-step operation. You drill a hole, then you tap it. But I guess probably the most important is it doesn't have the advantage of maximum material condition, right? As the hole gets larger, what are we really doing? We're positioning the pitch diameter. For positioning the pitch, The pitch does get larger and smaller, but probably on this size screw it's probably only 1,000th or so. So again, it's the centering effect of the screw. It's probably regardless of feature size. So 17 would be all you would get. But you noticed up here, and this is the clearance hole, you could have the advantage of maximum material. And as the hole gets larger here by a total of 9, that 9 you could have up to 21. So to make them about equal, what I do is I always give a tapped hole a little bit more. Sometimes I hear people saying the 60-40 rule, and that's all right as long as you know where the 60-40 rule came from. What you're trying to do is make it equal between the two parts, right? And that allows giving the tapped hole a little bit more. Now, when you have tapped holes, we're always going to do a projected tolerance zone. And a projected tolerance zone, why we do that is that, you know, if this hole happened to tilt within that zone, you see the hole could be in the right place here, but as it got out, if you put the screw in, or you put a stud, can you imagine the stud? The further out it got, the worse it would be. So this projected tolerance zone says that when we check this tapped hole, we want to check it at the face, and we want to check it out 502. And why we came up with 502, because that's the worst condition of the mating part. Up here it says that the size tolerance on here is 500 plus or minus 2, so the major size would be 502. That's our projected tolerance zone. All right, this here was our fixed and floating fastener. You may have to refer back to that at least initially. All right, the next thing I'd like to talk about is this companion program we have is the geometric stacks program. There is another workbook on the geometric tolerancing stacks that does some of the formulas. We are going to be doing some stacks in this program. We're going to apply the tolerancing, and I'm going to give you a goal. You always want to look in the beginning of the chapter. It's going to identify the goal, what is the end result that we're trying to achieve, and then in the end we're going to have to do a tolerance stack to make sure that we met those requirements. If you're not interested in a tolerance stack doing them, maybe you could just watch how I go about doing them. If you say, well, no, I really want to get involved and I want to do the tolerance stack, then you really need to have the companion program, which is the geometric tolerancing stacks. If you don't actually have the DVD or the video or the PowerPoint presentation, then you should at least have the workbook. It'll have the formulas and go through the problems yourself so you understand the principles. Because on the stacks, it was just too much to review. I thought I just couldn't add that much review in here so everybody would understand it. And sometimes, you know, we have engineers, they just a general knowledge of how it works, and if they really have to do it, then they can get out the book and do it. So I hope this review was good for you. It you know, just refreshed your memory on some of the things, and so I guess you should be prepared to begin in and roll up the sleeves, get down, and start working on some of our problems. So good luck on your problems, and we'll see you in the workshop problems.